competitions, including AMC's, and in 10th grade he made MOP, which is one of the most prestigious math summer camps you could make. And then in his 11th year, he won gold with the US in the International Linguistics Olympiad. So that's also very, very prestigious.
Silver. Or our team won gold. I won silver.
Yeah. Oh, that's still very good. Yeah. And then, so we're very honored to have him. And
all right, thank you for that. That was a lot. Let's see. Cool. I'm glad you guys are all here. This is. Let me just get a sense of. Raise your hand if you're in middle school. Okay. Raise your hand if you're in elementary school, or going to, or like the next year. Raise your hand if you're going to high school next year. Okay, cool. So the first, every time I've given this talk before, it has been for high schoolers. So just be aware of that. If you think I'm going too quickly, or if you have any questions, or if you're just totally confused, raise your hand, and I'll try to answer it. But yeah, please feel free to ask questions. Yeah, but we're gonna start off fairly simple here. So. First, I'm gonna define a couple of things so that we all are on the same page with what we're talking about. So I'm gonna tell you. I'm not actually gonna tell you exactly what this means, but I think you can work it out. I'm gonna define an n simplex, where n is some whole number from 0, 1, 2 all the way up. So an n simplex is basically the simplest, you can think simplex for simple, the simplest thing you can think of in n dimensions. So let's think, so if we're in 0 dimensions, what do you think a 0 simplex is? If you're in 0 dimensions, what's the simplest thing you can think of? A point. Someone said a point, yeah. Yeah, a point. I'm just gonna draw a point here. A 1 simplex. That's the simplest sort of thing you can think of in 2 dimensions. Yeah? A line. But actually, we're going to go with a line segment, right? Just a segment of a line. And you'll notice that, like, we'll keep going. 2 simplex. What's sort of the simplest shape you can think of in 2 dimensions? Yeah? A triangle. Nice. Yeah, and you'll probably notice a pattern here, which is that the number of points here keeps going up. So how many points do you think a 3 simplex will have? 4, and so what sort of 3-dimensional shape has 4 points? A tetrahedron, right? That's just a 3-dimensional version of a triangle. Okay, cool. And then we can keep going up. It might be weird to think of 4-dimensional shapes and 5-dimensional shapes, but it's basically the same idea. You have, so each n simplex has how many points? N plus 1 points. And all of these points are connected to each other, right? Like, all 3 of these are connected to each other, all 4 of these are connected to each other, and so on. And they live in n dimensions. Okay, and one other thing to notice here is that what are sort of the sides of a, let's say a 3 simplex. What are the sides of a 3 simplex? Yeah, basically, right? A tetrahedron, the sides are all triangles, right? So the sides of a 3 simplex are just 2 simplices. And if you look at this, the sides of a triangle of a 2 simplex are just 1 simplices, right? The side of a triangle is just a segment. Each side of the segment is just a point. And this pattern sort of keeps going this way. And one last thing, how many sides does each thing have? So how many sides does a tetrahedron have? 4, right? So 1, 2, 3, 4. There's 4 of them. And then a triangle has sort of 3 1 simplex sides, and line segment has 2 sort of 0 simplex sides. And instead of calling them sides, I'm going to call these faces. So basically, this is sort of an abbreviation, but a face of an n simplex is an n minus 1 simplex side. Okay, cool. And that's basically let's see. Oh, there's one more thing. So if we take any of these simplices, so here we have a big 2 simplex, right? This is a triangle. If we take this triangle, and I'm gonna start just saying triangle instead of 2 simplex because triangle is ironically simpler than that. So a triangle, this triangle is divided up into a bunch of smaller triangles, right? So, and this is a process called triangulation. So, and what you'll notice, one thing you'll notice is that you never in this sort of splitting up into small triangles do you see something that looks like this, right? Every triangle, either 2 triangles that are touching, if they're touching, they either only touch at a point at the corner, or their whole faces, or their whole edges are touching each other. You never see something like this. And that's basically what a triangulation means. Dividing up into a big end simplex into a bunch of smaller end simplices so that you don't have anything like this going on. Does that sort of make sense? Yeah. These are just, I'm throwing a bunch of words out there, but this is basically stuff you've probably like encountered before, if not under these names necessarily. Okay. And, okay, now I'm going to define something here. Now we're going to deal with something called Sperner's lemma. Now, a lemma is, can someone tell me what a lemma is? Does someone know what a lemma is? Yeah.
It's like a theorem, but like it's used for like a proof for another theorem.
Yeah, it's like a mini theorem, right? It's a step in proving a bigger theorem. And Sperner's lemma is one of my favorite lemmas. It in itself is like kind of cute, right? It's just a little thing that you can't really use, but it can be used to prove a lot of things. So, let's see. We're going to define something called a Sperner coloring. Now, Sperner's lemma is all about Sperner colorings. So, a Sperner coloring, Sperner coloring is a coloring, let's see, a way of coloring and triangulated n simplex with, okay, now one thing, let's see if we can figure out this width part here. So this is actually an example of a Sperner coloring. Now, you might notice I'm not actually using colors in case anyone's colorblind, so I'm using shapes instead. I'm using circles, triangles, and stars. So I'm using 3 colors here. So this is a 2 simplex, I'm using 3 colors. So in general, I'm going to color n simplices with n plus 1 colors, such that each face has a different forbidden color. Now remember, with a triangle, the faces are just the edges, right? The 3 edges here. And so each face has a different forbidden color. Can anyone, just by looking at this picture, guess what that might mean? Yeah?
Like a triangle, but meaning vertices are they're never all different.
That's actually going to be related to something else we're going to talk about here. But think about, parse this, yeah, so actually you're on the right track because you probably noticed something about this triangle. But we're going to get to that later. But basically, let's think about this. So each face, each of these edges has a different forbidden color. What do you think that means? Just look at these edges and how these edges are colored. In this case, labeled with shapes, but that's what I'm going to call a coloring. I know you know. Take a while. Does anyone notice anything? Forbidden. What do you think is forbidden from here? Let's see. We have a star, a circle, a circle, a circle, and a circle. What's missing? A triangle, right? There's no triangles. No triangles on this face, right? What's missing here? No stars. No stars. And what's missing here?
No circles.
No circles, yeah. And that's just what I mean by each face has a different forbidden color. Triangles are forbidden from this edge, stars are forbidden from this edge, and circles are forbidden from that edge. Everything makes sense so far? Cool. Okay. Yeah, and that's what Sperner coloring means. So this is an example of Sperner coloring. Now, why do we care about these Sperner colorings? Well, basically, what Sperner's lemma says is related to what you said. Can you say what you said again? Do you remember what you said? That's okay. You were looking at the smaller triangles, right? This Sperner coloring is a restriction on the big triangle, right? It's a restriction on the edges of the big triangle. So we might ask, what effect does that have on the smaller triangles? Well, if we look at these smaller triangles, we'll notice that, well, each small triangle has each of its three vertices colored with some color, right? This one has a circle, circle, triangle. This one has three triangles. And yeah, and there's actually one sort of special, one special shape here, and it's this one, this triangle here. And you'll notice what's special about this triangle. Yeah?
It has all three shapes.
Yeah, it has all three shapes, and what we're going to call these special triangles completely colored, right? This is actually, I don't think this is actually the official term for this, but it's something that makes sense to me. So I'm going to call these triangles completely colored. So a completely colored triangle is a triangle with labels on, with all three different labels on all three of its vertices. Does that make sense? Now, in this case, there's only one completely colored triangle, but you could easily create another completely colored triangle without breaking this Sperner restriction, right? So for example, we couldn't turn this into a star, right? Because stars are forbidden from here. But we could maybe turn this one into a star, and then we would have another completely colored triangle, right? Is that the only completely colored triangle? No, I made a couple, I made at least one, I think I made one more here, one more here, and one more here. So I actually made 1, 2, 3, 4 more completely colored triangles. In fact, you can have as many completely colored triangles as you want, but the question is there always a completely colored triangle? I'm going to turn this back. What was this before? I think it was a circle. I'll turn this back into a circle. And notice that this big triangle only has one completely colored triangle. So the question is, will there always be a completely colored triangle? Because we can see that it's possible that these are pretty rare, right? So if we have any coloring of any triangle, is there always necessarily a completely colored triangle? Now the answer to that question is no, because you could just color this with all circles, for example, right? But that's not a Sperner coloring, right? That's not allowed under this definition. So the question is this simple restriction, no triangles on this side, no stars on this side, no circles on this side, enough to guarantee that somewhere in here is a completely colored triangle? Question.
Can't you just make all the no triangles things with circles and no stars things with circles and no circles things with triangles and fill the rest with whatever you want?
Yes, that's exactly what I did. That's exactly what I did. Actually, I used, okay, yeah. Basically, yeah, you can try this on your own. Take a triangle, triangulate it. Only do circles and triangles on this side, only circles and stars, only triangles and stars. You can do that and then fill the rest in with whatever you want. But I'm gonna challenge you to try that and see if you can manage to avoid any completely colored triangles.
That's not what I meant. I mean like no stars whatsoever. Like only circles and circles that are no triangles and stars, and only triangles that are no circles.
That is an excellent question. Actually, that's a really good starting point, right? To start answering our question. That's not quite the direction I was going into, but let's explore that. So you're saying that we don't allow any stars, right?
Yes.
Is that possible? Let's see. Who said no? Did you say no?
Yeah.
You said, is that possible?
Yeah.
You said, yeah. But do you agree?
No, because you have to have a star on the corner, opposite the.
Yes, this one, right? There's an excellent observation, right? Because we forbid, that's its own past tense. Yes, we forbid triangles and circles from both of these, or we forbid triangles from this edge and circles from this edge. So can this be a triangle? No, because it's on this edge. Can this be a circle? No, because it's on this edge, so it can only be a star, right? And similarly, this can only be a circle, and this can only be a triangle. So automatically, we already have three things. And you might be saying, okay, well, that has to be a star. Can we just make everything else not stars? And you'll notice that if you do that, right? If you'll do that, this is going to end up, if this is your only star, what does this one have to be? Can't be a star, can't be a triangle, so that has to be a circle. What does this one have to be? Yeah, it can't be a circle, it can't be a star, so that's a triangle, and automatically we have our completely colored triangle, right? So yeah, that was a great attempt to try to find a counterexample, and you'll notice that that didn't work out. So now you're kind of suspicious. So this condition might have been stronger than you thought, right? This condition may in fact be enough to guarantee that there is a completely colored triangle, and I'm going to show you. And in fact, Sperner's lemma, this Sperner's lemma that is this tool that I talked about, that's exactly what Sperner's lemma says, although not quite. So what Sperner's lemma says, that's not a definition, that's a lemma. Sperner's lemma says that any Sperner coloring contains a completely colored triangle. Completely colored, not triangle, but small. Smaller. Smaller and simplex, yeah. Okay, and again, I welcome you to try this. Draw some other shape on your own, and label all the vertices, and see if you can actually show that this is the case, or see if you can ever like not have this be the case. Yeah, and this is what we're going to try to prove today. Any Sperner coloring contains a completely colored smaller and simplex. However, we're going to quickly find that this is actually a little tricky to prove, and this is a common trick in math. So when you find something that's hard to prove, sometimes you want to make it easier, but actually sometimes you want to make it a little more restrictive. And in fact, if you experiment a bit with this coloring, you'll find that it's not just the case that any Sperner coloring contains a completely colored triangle. It always contains an odd number of completely colored, smaller, and syntheses. Okay, now can someone tell me why does this guarantee that, so I'm saying that it contains an odd number of smaller and syntheses. Why does that guarantee that there's always at least one? Yeah.
Because 0 is not an odd number.
Exactly. 0 is not an odd number, so there can't be 0 of them, there has to be 1 of them, or 3 of them, or 5 of them, or so on. Right? So, in fact, this will be enough to show that there's always 1. Cool. Let's start proving this. Okay. Let's see. I'm going to erase some stuff. Does everyone understand the definition of Sperner color? Anyone have any questions at this point? Okay, I'm going to erase this part. I'm going to erase this part. And, yeah. And remember, we want to show this for any then, right? Any Sperner coloring, really I should write, any Sperner coloring of and simplex contains an odd number of completely colored smaller n syntheses. So we want to show this for every n. So where should we start with? If we want to show something for every whole number starting from something, where should we start with? What's our starting point?
Start with 0.
Start with 0, except with 0 simplex is really boring, it's just a point, so we're actually going to start with 1. So we're going to start with n equals 1. And this is something called a proof by induction. Raise your hand if you know what a proof by induction means. Okay, so basically what we're going to do is, we're going to do a proof that's kind of like, so what we're going to show is, we're going to show that this is true for n equals 1, and then we're going to use the fact that it's true for something smaller to show that it's true for something larger. And I'll show you what I mean in a second. So let's start with n equals 1. So, okay, n equals 1, what's a 1 simplex?
A line.
A line segment, right? So we have a line segment. How do we triangulate a line segment? Well, we have to break it up into a bunch of smaller line segments. Okay? And now we want to do this Sperner coloring. We want to find a Sperner coloring. Let's use the colors circle and triangle. And okay, and we're going to forbid no triangles here, no circles here. Because remember, for a line segment, its faces are just the two endpoints, right? So forbidding triangles from one face and forbidding circles from another face really just forbids them from the two endpoints, right? Okay. So now, now let's color this, right? So if we forbid triangles here, what has to go here?
Well,
A circle. If we forbid circles here, what has to go here?
triangle.
A triangle. And let's just fill in the rest. Someone call out, can you call out a shape for here? Triangle. Circle. Let's draw that. Circle. Triangle. What'd you say? Circle. That's a lot of triangle. And I'm just going to put another triangle here. Okay. Now, is it true that this has an odd number of completely colored end simplices? Let's break down what that means. An end simplex here is just a line segment. Is it true that this thing here has an odd number of completely colored line segments? So completely colored, in this case, what would completely colored be? Yeah, it has to have a circle and a triangle, right? But it could be in this order, or it could be in the other order, right? It could be a triangle and a circle. Okay. How many of these are there? Yeah, we have one, 2, 3. 3 of these. How many of these are there?
2.
We have 1, 2. Okay. Are there an odd number total?
Yeah.
Yes. Okay. Cool. Now I want you to stare at this for a bit, and remember, we can change this to anything, right? We can replace this with a circle, we can change these all to triangles except for the first one, and we can fiddle around with this, and I just want everyone to stare at this for a moment and think about why there has to be an odd number of completely colored end simplices. Stare at this for a moment and think about it. And I know some of you probably see it right away, for some of you it might take a bit, but think about why there should be an odd number of completely colored line segments. Give everyone a moment to think about that. You can play around a bit, right? Draw some things out, right? Like maybe start with something dumb, right? What if we just have a circle and triangle like that? What if we had a couple things in between? Or what if that's a triangle? Okay. Okay, so I'm going to suggest the way you want to think about this is start from this end and keep going down the line. So you start with a circle, and you go, and at some point you end up with a triangle. Okay, can someone tell me, someone think they know why there has to be an odd number of these? Yes.
We could use induction for a small line and continue to use it for a big line.
We could. There's something similar than that, though. Yeah?
So because if you have like 2 or 4 or 6 numbers of like those completely colored triangle, so like if I say like that line starts with O, and you have like 2 like completely colored triangles. So it would always go back to O, so it won't go back to triangle.
Yeah, that's basically the right idea. So, I'm gonna rephrase that a little. So, pretend you're standing here, right? Pretend you're starting here. You have a circle, right? And at some point, you start with a circle, and you actually don't know what any of these are yet, but you know that you end up with a triangle, right? So at some point you want to switch from a circle to a triangle. So, how are you going to do that? Well, that means at some, that means if you switch from a circle to a triangle, there has to be a point where you actually make that switch, right? There has to be a point where you actually switch from circle to triangle, right? Now, so at some point you go from a circle to a triangle. And that point where you make that switch, what is this?
1.
This is just, yeah, this is just the one of the completely colored segments, right? Now, you might, but the problem is you might not, this might not be it, right? You might switch from a circle to a triangle, but then you might switch back to a circle, right? But that's no problem, because you know that you always end up with a triangle, right? So if you switch to a circle, well, you have to switch back to a triangle by the end. And if you switch to a circle again, you again have to switch back to a triangle by the end. Now, if you had an even number of switches, right? If you switched from circle to triangle, back to triangle to circle, an even number of times, what would you end up with?
Circle.
You'd end up with a circle at the end, right? So you need to switch an odd number of times to go from a circle to a triangle. Does that make sense to everyone? And each of these switches happens at a line segment, right? So a circle, triangle, triangle, circle, this might still be a circle, and circle, triangle. Each of these switches happens at a line segment, and since we know that there has to be an odd number of switches, that means there's an odd number of segments. Sorry, each of these switches happens at a segment that is completely colored, and since there's an odd number of switches, there's an odd number of completely colored segments. Does that make sense? Okay, so we're done with the n equals 1 case. We've proved the n equals 1 case. Does that make sense, everyone? Are there any questions? Cool. Okay, we're building this step by step, and that's sort of the idea of a proof by induction. Let me write that word down for people who don't know. Yeah, so a proof by induction starts with something small. For example, n equals 1, and it builds up from there. And instead of just going one by one, going n equals 1, then n equals 2, then n equals 3, then n equals 4, we're going to do everything in one go by showing that if you can prove something for n, if you can prove this is true for n, you can prove it's true for n plus 1. So really, a proof by induction has a base and a sort of machine, right? You start by laying the foundation. You start with a base. You prove it for n equals 1. And you have a machine that converts every proof for n to a proof for n plus 1. So so this machine you can apply it once to get a proof for n equals 2. You can apply it again to get a proof for n equals 3. And you can keep applying this machine, and because you've proven it for this general machine, you can prove it for every positive n. Does that make sense? Yeah, I'm going to show you what that actually entails. But the thing is, this proof by induction, the way I'm going to show it isn't actually quite the most general thing. I'm actually going to show you how you can get from 1 to 2. And it should be pretty clear from there, and I'll sketch out how you can get from 2 to 3. And it should be pretty clear from there how you can get to each step, how this generalizes for each step. And I'll show you what I mean. Okay, but we've proven this for n equals 1. Now, the idea of a proof by induction is to use this smaller thing to prove this bigger thing. And what you want to search for is, you want to search for where the smaller thing shows up in this bigger thing. So how does a 1 simplex, a Sperner-colored 1 simplex, show up in this Sperner-colored 2 simplex? Do you see anywhere where you have something like this in here? And by something like this, I mean a coloring that forbids triangles here and forbids circles on this side of an edge. Yes?
Edges.
Yeah, these edges, right? Each of these edges is a mini sort of Sperner coloring, right? And that's why I talked about faces so much, because this faces is the crucial step, right? The induction works by looking at each face and showing that, well, if it works for the faces, then it's going to have to work for the whole thing. Now I say it works for each face. In fact, we actually only really need to concentrate on one face, right? So I'll show you what I mean. Okay, we showed that, okay. Let's just focus on this bottom one, because we use the same colorings here, right? We use the circles and triangles, the circles and triangles. So first, we note that this really is just a Sperner coloring of a 1 simplex, right? Because what's forbidden from this point?
Triangles and stars.
Triangles and stars,
And
right? Stars are forbidden from everywhere, so we don't even have to worry about stars. But specifically, triangles are forbidden from here. No triangle, and circles are forbidden from here. No circles. So this line segment in itself, which only has circles and triangles, is an example of a Sperner coloring of a 1 simplex, right? In this bigger 2 simplex. So what can you deduce from what we already proved? Yeah? Yeah.
Maybe like build it up with a triangle.
Okay, yeah, but what can we, how can we use what we already proved here? Like, what does what we already proved tell us about this? Yeah?
There's an odd number of completely colored.
Yes, there's an odd number of completely colored segments here, right? And in here, completely colored is just the circle triangle coloring, right? Let's make sure there's an odd number. There's one here. There's one, I'm just gonna mark it like that. There's one here, and there's one, minus one here. Right, there's an odd number of them, right? I think those are the only ones. 1, 2, 3. Okay, yeah, that's an odd number. So, okay, cool. So just by applying the n equals 1 case to the n equals 2 case, we already know that there's going to be an odd number of triangle circles here. Okay. Now let's think about what that means, right? But we don't want just the circle triangles, right? What we're looking for are the completely colored circle triangle stars, right? But we're almost there, right? If we can find the circle triangle segments, all we need is just for the circle triangle segment to have a star on top, right? That's really all we need. Does this one have a star on top? Does this one have a star on top? Does this one have a star on top? That's unfortunate. So we can't, let's say we don't know where this is yet. We can't actually, so while we're kind of close to finding a completely colored triangle, if only there was a star on top, we can't guarantee that any of these have stars on top. So now maybe we might be stuck. But let's think, okay, if it doesn't have a star on top, what must it have on top? Either a circle or a triangle, right? Okay, so that means that, okay, we can, okay, so we have this original circle triangle. We don't necessarily have a star on top. We could have a circle or a triangle on top. But remember, like, one thing you want to notice is now, if we have a circle on top, we get another circle triangle segment, right? And if we have a triangle on top, we get another circle triangle segment here. And that's interesting. Yeah?
But aren't stars allowed on this line? Like we're not on a no stars line anymore. We're one thing above it. So aren't stars allowed now?
Yes, stars are allowed now, but we want to guarantee that we can find something like this, right? We want to guarantee that we find this. So, in fact, yeah, I could replace this with a star, but the problem is, in order to prove this, we have to pretend that, okay, this might not necessarily be a star. Does that sort of make sense?
But like, what if there are two stars on top of one triangle or circle? For example, let's say the triangles over there were stars.
Yeah, and then we'd be done, right? Then we will have found.
What if it's two stars and one like, for example, the triangle over there.
This one?
No, the one next to it.
This one?
Yeah. What if the two triangles were stars?
These two triangles?
What if they were stars?
Then we'd have a circle, triangle, star triangle, and we'd be done,
True.
right? Yeah. But the problem is we don't know that that's necessarily true, so we're going to have to look for it. Okay, and this is the part where I'm going to sort of give away how we're actually going to go about proving this. So it seems like these circle triangle segments are important, right? So let's just find all of them. This might take a while. Let me know if I miss any, but I'm going to find all the circle triangle segments, and I'm just going to mark them like this. That's a circle triangle, that's a circle triangle, circle triangle, circle triangle, circle triangle, circle triangle. Anyone up here? Circle triangle. Let me. Where's my black marker? There's my black marker. Circle triangle. Actually, I'm gonna do something a little weird here. I want to do this. Yeah, I'm gonna Yeah, actually, no, that's fine. Okay, circle, triangle, circle, triangle, circle, triangle, circle, triangle, circle, triangle, circle, triangle, and yeah, if anyone sees, does anyone see any other?
In
the middle.
Ah,
To the
circle,
right.
triangle,
No, the bottom.
circle, triangle,
As it's supposed to.
circle, triangle,
The middle to
circle,
the
triangle.
bottom. Bottom.
Is that or that's a
Bottom.
circle?
Bottom.
Bottom. Bottom, yeah. Bottom, middle one.
I got these.
Bottom
To the right. To the right.
Got that, I got that.
To the right.
triangle.
To the right. To the right. To the center. No.
Oh, yes, there we go, that one, yeah. Did I get all of them?
Circle, circle, circle. It's a circle, circle.
Oh, yeah, that's not a, yes, I did that wrong. I think that's all of them. Okay, cool. So we marked all of these, and I'm just gonna emphasize this a little. And what I'm actually doing is, I'm sort of breaking these open, right? So pretend these are like trapdoors, right? You have all of these walls, and I'm gonna cut all of these trapdoors in here. In every circle triangle segment, I'm gonna cut a trapdoor. Okay. Cool. Now, the one thing we already showed was that there are an odd number of trapdoors here, right? That's the one thing we proved from the smaller case. That's our sort of inductive, it's called an inductive hypothesis. That's what we already assumed, because we already know that this is true for the smaller case. Okay, so we know that there's an odd number. And now what we're gonna do is we're gonna follow these trapdoors, right? There's a trapdoor here. Now, what can happen, right? We said that if there's a trapdoor in a triangle, right? Either the top thing is a star, in which case we're done, we have a completely colored triangle, or one of these things happens, right? Either this thing happens or this thing happens, either the top one is a circle or a triangle, in which case there's gonna be a second trapdoor, right? Can you ever have 3 trapdoors in one triangle? This is completely colored, it only has 1 trapdoor. Right, let's think about this, right? Having 3 trapdoors would mean that this is a circle and a triangle, or the other way around. That's just symmetrical. And this being a trapdoor means that this is a triangle, but this being a trapdoor means that this is a circle. Those can't both happen, right? So you can never have 3 trapdoors. You either only have 2, in which case you have the circle triangle and the circle, or the circle triangle and the triangle, or you only have 1, in which case you have the completely colored triangle. Right? Okay. Let's follow these trapdoors. But yeah. What this means is that each thing only has 1 or 2 trapdoors, meaning that we can either go through them, right? We can go through the 2 trapdoors, or we hit a dead end, right? But we actually like dead ends, because dead ends means that we found our completely colored triangles. Let's start going. Okay, so actually, let's start here, right? We go in through here, a circle triangle. We hit another trapdoor. So we're not at a completely colored triangle yet. Through another trapdoor, still not at a completely colored triangle. We keep going, we keep following these trapdoors until, aha, we are stuck. What do we end at? A completely colored triangle. And that's it. That's exactly what we want. There's a problem. Yeah?
Like, is it because you could, like, get out to an edge?
Yeah. You might get out, right? Let's see what else might happen.
But you can't really get out because there can't be a circle and a triangle over under no triangles or no circles, and you started at a no stars. So unless you turn, oh, never mind.
Yeah. But that's exactly it, right? Okay. So yeah, no, you're on exactly the right track, right? The thing is, right? We think we found a proof. Once we think we found a proof, we're gonna think, okay, how do we even screw this up? How can we screw up here? So we could end up here, but something bad might happen, right? We might not hit a dead end, right? Do you have a comment?
Yeah, if you go through the first
Yeah.
gate, you'll go out.
Yeah, that's the problem, right? We might not find a dead end. We might just go right out, right? But you pointed out that we can't, if we go out, where are we gonna end up? So we have to go through a circle triangle to get in, and a circle triangle to get out. Can we go out through here? No, because there's no triangles here, right? So there can't be any circle triangles, so there can't be any trapdoors. Can we go out through here? Again, no circles, so no trapdoors. So if we go in and go out, we have to go in a circle triangle down here and a circle triangle down here. And finally, can we go out, like, go in and out through, like, the same triangle? No, it doesn't work like that, right? Because each triangle only has the two trapdoors. Two or one, in which case we hit a dead end. But that means there's only really one path, and it can't really intersect with itself, or it's going to end up with, like, 3 trapdoors, right? Unless you're backtracking or something. So, what does this mean? Oh, another thing that can happen. You might see it's going on right here, right? This is really weird. You might have a situation where you have something like this going on, where it's like a path that like never ends, right? You might have a cycle here, right? Or in some cases, I'm actually going to change this to a triangle to demonstrate. In some cases, you might actually have a path in the middle that sort of starts somewhere and never ends somewhere, right? Yeah. But you can convince yourself that this is basically everything that can happen, right? You can have a path that starts, your path is either going to start out here or in here, right? If your path starts out here, it's either going to hit a dead end or it's going to come out through here. If your path starts in here, it's either going to hit a dead end both ways or it's going to cycle in on itself. That's really all that can happen, and that's important, right? You have to convince yourself that this is exactly all that can happen. Yeah?
But there's an odd number over there, so for every pair of 2 U-turns, there must be at least one that does not have a partner in U-turning business.
Yes! Now we use what we just proved, right? We know there's an odd number of trapdoors here, right? And remember, what we're worried about is something that goes in this way and out this way. But each of these accounts for a pair of trapdoors here, right? So for every path that goes in and out, we're going to have like a pair of trapdoors. So I'm going to call these in and out paths, like the burgers. And the in and out paths, they don't have, and they account for, and each of these accounts for a pair of circle triangle edges, right? And so if we add up all of these in and out paths, we go through how many circle triangle edges. Sorry, let me rephrase that. If we, there might be more in and out paths, but all of these in and out paths taken together, they are only going to go through a bunch of pairs of circle triangle edges, right? So they're only ever going to go through an even number of circle triangle edges down here. But there's an odd number of them, right? So if we subtract off, if we take an odd number, we subtract off a bunch of pairs, what are we going to end up with? Still an odd number, right? So no matter how many in and out paths we have, they're all gonna, we're only ever gonna be subtracting circle triangles in pairs, so we're still gonna have an odd number of circle triangle edges down here. And those odd number of circle triangle edges, they're gonna be the dead end paths, right? Because they're not in and out paths, they have to be dead end paths. So since there's an odd number remaining, and all of those are gonna hit dead ends, there's gonna be an odd number of completely colored triangles. That makes sense? That only takes care of the paths that go in from down here, right? What about the paths in here? The circle paths. How many complete triangles are here? 0, because there's no dead ends, so there's no, remember, each dead end is a completely colored triangle. Each completely colored triangle is a dead end. There's no dead ends, there are 0 completely colored triangles. What about here? It's going to start somewhere and end somewhere. How many dead ends is it going to have? 2. It's going to have 1 here and 1 here. So that's going to be 2. So each of these is going to give you 2 completely colored triangles. So, in summary, you have each of the inner things are going to give you either 0 or 2 completely colored triangles. So all of the inner things are going to give you an even number of completely colored triangles, right? From the inner ones, right? Whereas the outer ones, the ones that go in and out, this is going to give you an odd number of completely colored triangles, right? Add this up, an even number plus an odd number is what?
Odd number.
An odd number. And so, in total, there has to be an odd number of completely colored triangles. This one here, plus this 2 here, this is an odd number plus an even number, That's an odd number. Does that make sense? Any questions? I know there's a lot of things to keep track of, but really the basic idea is pretty simple. You follow these paths, the paths are going to go in and out or get stuck, and every time it gets stuck, it's going to give you a completely colored triangle, and you can only get stuck an odd number of times because there's only an odd number of entrances and exits here. Cool. Now, we've shown the n equals 2 case. And I claim that this actually shows all of the cases, right? Because from n equals 2, you can actually build up to n equals 3 in a similar way. And I'm only going to sketch it out here. You can sort of finish this. You can finish this yourself. But basically what happens is the n equals 3 case, you have a tetrahedron. Each face of this tetrahedron is a what?
No.
It's a triangle. Now what's happening here is you're forbidding, let's say you're forbidding from this face, you're forbidding no circles, no triangles, no stars, and no, I'm going to do downward triangles, right? And so what's going to happen is, let's see, there's no stars, no circles, and no triangles, so this, no downward triangles, so this has to be an upward, oh no, I've completely, let's say this is the left face, this is the right, no, this is the bottom face, this is the right face, and this is the back face. Let's see, so no left, no bottom, no right, so this is going to be a star, right? This is going to have to be a circle. This is going to have to be not the bottom one, which is the downward triangle, and this is going to have to be an upward triangle. And what you notice is that each of the faces, in fact, this bottom face here is exactly what we have here, right? We've forbidden small or downward triangles from this entire face, and we've also forbidden circles from this edge, upward triangles from this edge, and stars from that edge. So here, that is just this, right? And we showed that there's an odd number of completely colored triangles here, right? There's an odd number of these. And now, to generalize that proof, we turn these into our trapdoors. So now we have two-dimensional trapdoors. And so what happens is we're going to have an odd number of trapdoors here, and once again, we can go in and out, or we get stuck here, or we have a cycle somewhere in here, or we have something stuck here. And you'll notice that the places where we get trapped are exactly, let's see, so we'll have a trapdoor on one end and no exiting trapdoor, and the only way you don't have a trapdoor is if this is the last remaining color, and that's our completely colored tetrahedron. So again, there's an odd number of completely colored tetrahedrons, and this keeps going. You can keep finding these trapdoors, keep finding these paths, keep building up. That's the proof by induction. So it works for 1, you can show that you can get from n to n plus 1, because it works for everything. Okay, I went through that pretty quickly, and you're going to want to go over this when you get home and like think through this, but that's basically the idea. Any questions about that? Cool, okay. Now you might be wondering, where's the cake? Here's the cake, and it's a really weird cake. And yeah, I took a bunch of smaller cakes and sort of like did like a mishmash of this, and this is yeah, we're trying to split cake here, right? So how do we split cake with this? So what's our problem? We have a cake. We have this cake here, and it's kind of weird. It's kind of weirdly shaped. It looks like this. And we have a bunch of friends. Let's say we have n friends. And these n friends want to divide up this cake into n different pieces. So let's say n equals 3, for example, and so we can divide up, we want to divide up this cake into 3 pieces. And each of these friends is going to have a favorite piece. Let's say our friends are A, B, and C. Let's say friend A's favorite piece is this piece, right? Friend B's favorite piece is this piece. And we're thinking, okay, maybe everything will work out, but what if friend C's favorite piece is this piece? Then we have a problem, right? They don't each get their favorite piece. Someone's going to be upset. So what we want is a way to divide up this cake so that every friend gets their favorite piece. So that every friend can get their favorite piece. Basically, so that every friend's favorite piece is a different piece. So that everyone is happy. Does that make sense? Now, what Sperner's lemma will help us show is that this is always possible. And this might be a little surprising because the cake can be really, really weird, like that cake there. But this is always going to be possible, assuming 2 things. So theorem. There is always an envy-free division of any resource, any positive resource really. Envy-free, and by envy-free I mean no one is envious of each other. No one is jealous of another person's piece. Assuming 2 things. 1, everyone is hungry. And no one has any dietary restrictions. By the way, are there any dietary restrictions here? Raise your hand if you're like allergic to like nuts or don't eat dairy or something. Okay, I have peaches for you if you don't want cake. If you can't have cake. But we'll get to that later. Everyone is hungry. Or, sorry, that's one step. So basically what this means is that everyone would rather have cake than no cake, right? So no one's gonna be like, nah, I don't, I would want like a piece with like no cake rather than a piece with cake, right? So everyone is hungry. And 2, there are no sprinkles. And you'll notice that there aren't any sprinkles on this cake. There's a bunch of like, there's some like weird little flakes, but there aren't any sprinkles. And what this means is that no one's gonna be so picky that they're gonna be bothered by a single sprinkle. And another way of phrasing this is everyone will be okay with a piece plus or minus a crumb. So, or a sprinkle, right? So, if there is some small number that everyone agrees on, that if the knife sways like a tiny bit, but it's still within that small number, no one's gonna be like, oh, I immediately hate this piece now. If I change this a tiny bit, C's not gonna be suddenly like, oh, I don't want this piece now, I want this piece. So that's not gonna happen. And we're gonna guarantee that that's not gonna happen. And as long as that doesn't happen, as long as nothing crazy like that happens, then there is going to be a fair division, an envy-free division. And I'm going to show you how in these few minutes, and hopefully we can actually try this out. Okay, I'm going to erase these trapdoors. I'm not going to erase Sperner's lemma because that's going to be important. Now, since we proved Sperner's lemma for the n equals 2 case, for 2 simplicities, we're actually going to just use this case. And this actually corresponds to the 3 friends case here. So we're going to prove this for 3 friends, but since Sperner's lemma works for any number, this also works for any number. Okay. Now I claim, again, I'm going to do something weird. I'm going to actually claim that I can prove a stronger result. That will actually make my life easier. So I claim that I really only need 2 vertical knives. And I'm going to represent this with, if I can find it somewhere. Yes. 2 vertical chopsticks. So, I'm just going to split the cake like this, right? I've split it into 3 different pieces, right? And I'm going to call this left piece the X piece. this piece the y piece, and this piece the z piece. Okay? And what this is going to mean is that, let's see, and this plate is about 30 centimeters long. So we're going to have x plus y plus z equals however long this cake is, right? And I'm just going to say that this is one cake unit of length. So x plus y plus z equals 1. So basically what this means is that if you give me three numbers, if you give me three non-negative numbers that add up to 1, that tells me how to cut up the cake, right? If you tell me 1/3, 1/6, 1/2, that's how I'm going to cut up the cake. I'm going to put like 1/2 here, and then divide this up so that it's like 1/3 and 1/6, and that's the cake. That's the cut set of this cake. That's how I'm cutting this cake. So any triple x, y, z that adds up to 1 tells me how to cut the cake. Now you might notice that z is actually kind of redundant here, right? Because if you know x and y, you know z, because all three add up to 1. So let's graph this. What does this look like? I have x, and we have y. And so x plus y plus z equals 1. Z is a little redundant, so what this really means is that x plus y is less than or equal to 1, right? And whatever's remaining is the z. So I'm going to draw the graph of x plus y is less than or equal to 1 with something like this, right? What's this point here? Someone tell me? Yeah?
Is it
1, 0, right? Yeah, this is 1, 0. And this is 0, 1. And we're looking at everything down here, right? This is 0, 0. And I'm actually just going to write in the z value too. So here z is 0, here z is 1, here z is 0, so that everything adds up to 1, right? Now you might notice that now we have a triangle. And now every point in this triangle is a way of cutting the cake. Now this might be something like 1, maybe 0.2, maybe 0.7, and 0.1. That's way off scale. But let's say that's how it is, and that tells us how a certain way to cut the cake. This slice should be 0.2 of the width, this slice should be 0.7, this slice should be 0.1. Okay, so every point corresponds to a way to cut up the cake. And remember this thing, right? Everyone will be okay with a piece plus or minus a crumb. In this case, I'm actually just going to do a centimeter, but basically you can go as small as you want. And basically what you can do is you can start triangulating this triangle. You can start making these little segments, these little smaller triangles. And you can keep going, and eventually you get everything. And you're going to end up with something like this, right? You're going to end up with a triangulated triangle. Now I actually sort of squished this a little this way, so it's a little more equilateral. But basically these are still the same points. 0, 0, 1 down here. 1, 0, 0 down here, and 0, 1, 0 up here. And now we have a way of modeling our problem, right? Because every point in here corresponds to some way of cutting the cake, right? So this is probably going to be 0, maybe 1, 2, 3, 4, 5, 6, 7. This is like no, this is 1/7. I can't do math. 0 and 6/7, right? That's what that point is. And each point corresponds to some three numbers that add up to 1. Okay. Now you might have noticed that I actually labeled these ahead of time with a bunch of letters. Now notice that this is not a Sperner coloring, right? I just labeled these with letters. These are the friends. The friends' names are Alice, Bob, and Cal, let's say. And A, B, and C. And they, I've labeled each point with one of their names so that each individual triangle has all three names, right? An A, a B, and a C. And this will come in handy later. And what we're going to do is we're going to start asking each of these people what slice of cake they want. Let's start down here. Actually, let's just start with C here, right? Let's ask C. Let's say we're cutting the cake in this way. That would probably correspond to 2/7, 1/7, and 4 7s. Something like that. I think that works. I think I'm totally wrong, but that, let's see, am I right? Yes, yeah, okay, that's right. Okay, so C, okay, and this corresponds to a certain way of cutting the cake, right? This is 2 7s, this is way off scale. Let me make it more like that. This is 2 7s, this is 1 7, this is 4 7s. We're gonna ask C, which piece of cake do you prefer? Now C might answer this one because it's the biggest, C might answer this one because it's got this little carrot thing on it. But yeah, regardless of what C answers, C is gonna answer either X, Y, or Z, right? Remember, these coordinates, these are the 3 coordinates, each slice is one of these 3 coordinates, right? Now we're gonna assign a color to each of X, Y, and Z. We're gonna say that X is a, let's make it a triangle, Y a circle, and Z a star. Okay, let's say C says that Z is his favorite piece. And so, we're gonna label C star. And let's say A says right here, maybe we move the knife a bit, that his favorite piece is also a star. We're gonna label that, right? It's his favorite piece is also this piece. Does everyone get what we're doing, right? We're picking each point. Each point tells us a way to cut the cake with an X, a Y, and a Z. And we ask the person the point is labeled with whether they prefer the X piece, the Y piece, or the Z piece, and whichever they answer, we color that point with either a triangle, a circle, or a star. And so we're going to color everything with either a triangle, a circle, or a star. What's special about this coloring? What kind of coloring will this end up being? You can probably guess just by the fact that I asked this question. Yeah? You think it will be a Sperner coloring. Now remember, a Sperner coloring doesn't have that many restrictions. All it says is that one color is forbidden from this side, one color is forbidden from this side, and one color is forbidden from this side. And yeah, and remember that what that tells us is that each of these vertices are sort of fixed, right? There's only one thing. Let's see if that's true here. Down here, let's just look at B first. This point here. We have 0, 0, 1. What is that? What is that cut? So this is a really weird cut. This is putting the first knife here, the second knife also here,
On top.
and then the last piece is just the whole cake, right? 0, 0, 1. So that's X, Y is no cake, Z is the whole cake. Which piece is B gonna pick?
Could be.
Z. Why?
Because B is hungry.
Because everyone is hungry. Yes, because B is hungry. So he's gonna pick the whole cake instead of
What
nothing.
if B is a girl?
Right? So B's gonna pick the whole cake, the Z, so that's a star. Right? Let's ask C down here. What's she gonna pick?
I hate
Let's see. Let's see. So here,
Cow.
the whole piece is gonna be X, Y, and Z are gonna be empty. So what's C gonna pick?
X.
X. She'll pick X, and so she will get a X, which is a triangle. Right there. Hey, what are they gonna pick? 0, 1, 0.
Y.
One of the knives goes here, one of the knives goes here. This is the Y piece, that's the whole cake. A's gonna pick
Y.
Y, which is the circle, right? This seems to be going along as planned. So what color do we think is forbidden from this edge? A circle. No circle. Is that true? Why is this no circles? Yeah,
You always
what
have
is
zero.
this line? This
You
is the
always have
x-axis
zero.
actually. And in here, y is 0, right? Y is 0. The middle piece is always empty, so no one's gonna pick the middle piece, right? Everyone's gonna pick either the left piece or the right piece, X or Z, triangle or star. Everything's either gonna be a star or a triangle, and no circles on this side. Here, what's forbidden? A triangle. No triangles, because which variable is always 0? X, right? This is actually the y-axis. So the left piece is always empty, no x's, no triangles. Similarly, no stars. And so, this is a Sperner's coloring, right? This is a Sperner coloring. Now there's only one thing we know about Sperner colorings, and what is that? Sperner's lemma. There is an odd number of completely colored, smaller end simplices. And in this case, we actually don't care that there's an odd number. We're going to use the fact that there always is one.
At
So
least.
somewhere in here, we're going to find a sum piece with all three colors. Now let's see what's going on here. I'm going to load this up a bit. We have C, A, B, and all three colors are going to be different. Remember, we already know that all three people are different, right? That's how we labeled these points. So we have a circle,
Different.
a triangle, a star. So maybe this corresponds to cutting the cake like that. And this is the triangle, circle, star. Okay? C's favorite piece. Okay, or actually, yeah, let's think about this a little, right? So C's favorite piece here at this point is the circle piece. B's favorite piece here is the star piece. A's favorite piece here is the triangle piece. But remember, we did something at the very beginning, right? We made these triangles really, really small, right? And what we can say is that we can make the triangles so small that they are so small that it avoids this crumb thing, right? You can make these triangles like so small that it's like each thing really only moves a very tiny bit that's less than a crumb, or less than 1 centimeter, or less than whatever your threshold is. And so that there isn't really any big difference between these 3 points. To all of them, it's practically the same. So really, this whole triangle gives us one cut, plus or minus a crumb, right? It tells us a cut, and you might have to adjust this a tiny bit for each one, but everyone has already agreed that that length, the tiny length that we cut this triangle into, is negligible. And so, this whole triangle really only corresponds to a single cut, plus or minus a crumb. And so A's favorite piece is the triangle, B's favorite piece is the star, C's favorite piece is the circle, and this is our envy-free division of cake question.
In that case, A, B, C's personality, or like they have to be different for all the triangles. Like for the first triangle, A, B, C is a different person, and the last triangle, A, B, C is a different person.
Yeah, so we labeled each point with a person, right? So we're asking different people here, right? Here we're asking B what your favorite piece is, and we're labeling it. Here we're asking C what their favorite piece is, and we're labeling it, right?
That B has to be different from the other B in the other triangle.
Sorry, I'm not quite sure.
So like they all like okay, mathematically sure, like there can be a chance that the ABC that will can fairly get. Oh, never mind.
Are you sure? Okay, right, I think, yeah, like this B is different from this B, like these are the same B's, but they're different cuts, right? So because of a different way of cutting it, they're gonna change it up, right? So these aren't gonna be the same colors, right? That's one thing. Yeah, any questions?
But each side is A, B, or C. That means each triangle has one of each. So even if they're gonna change, they're like, at least one's gonna be circle, star, and triangle, and it's gonna have all A, B, and C. You can use a different method to prove that if you triangulate a triangle, then each triangle has an A, B, and a C point. That's a different method, but I'm pretty sure it can be proven since you just did that over there.
Well, so basically what happens is if we don't have, right, if we have A, B, and C labeled for every triangle, but if we don't have a Sperner coloring, right, if every single triangle doesn't have all 3 colors, right, if it's something like this, everyone is always going to fight over a piece, right? We need the Sperner color, we need this completely colored triangle so that everyone picks a different
That's
piece.
literally what I was saying.
Does that make sense?
That was
Okay.
literally what I was saying.
Okay, cool. Just check. Okay, any other questions? But yeah, so we proved this. Does that make sense? Okay, now in fact we proved something more, right? This is really interesting because a lot of times in math, you only ever prove that something exists, right? This happens all the time. Like, once you go up to calculus, you will learn like the intermediate value theorem, which will tell you that at some point, something will exist. But you don't know where. But this proof actually tells you where it'll happen, right? Because it tells you because of this trapdoor thing we did, right? We can find the completely colored triangle by drawing these trapdoors and by following the trapdoors. And we might end up coming out again, but as long as we end up somewhere, we'll find the actual Sperner's coloring. So in theory, you can actually implement this, right? You can actually make this happen in real life. It doesn't just tell you that one exists, it tells you how you could find it. And in the 15 minutes that we have left, I'm gonna try to demonstrate this. And I've never done this before. I've never seen people do this with real cake before, but basically I need 3 volunteers who either have no dietary restrictions or is willing to have a representative pick a piece of cake for them. Or be someone. Let's see, I need 3 volunteers. You wanna come up? Sure. You wanna come up? Okay. You're allergic to, sorry. Let's see. Are you allergic to nuts? You said?
No. I said not.
No, not you. You're allergic to nuts. That's okay. Can you actually come up with a partner? Can someone else come up? One more person. You wanna go? Okay. You wanna go? Okay, so he's gonna pick for you actually. So just pick whichever one looks the nicest. And I'll give you a peach at the end. Okay, so come up if you want one. Come up here. And I want you to come around this way so we can all see. Come on this side. Okay. Let's see. I know you, right? Yeah. I TA'd for you once. What's your name again? Inia. Okay, right. I'm gonna call you person A, right? You're gonna be person A. And what's your name?
I know it's an IBC.
Sure, you can be person C, and you're Leo. Okay, you're gonna be person B. So this is actually Inia. This is actually Leo. This is actually a new name. Okay, cool. Okay. Let's see. Let's try to make this work. So, again, I've never done this. I've never actually done this before, but in theory, we just proved that this is possible. So this should work out. So we're gonna start at this point here, right? Because remember, we want to find all the trapdoors, right? And we want to start finding a trapdoor, and the easiest way to find a trapdoor is to just start searching down here. Okay, let's see what happens. So let's start at this point here. And let's say we labeled this with a B, right? And actually, I'm not going to draw the whole triangle, I'm just going to build it up bit by bit. So we labeled this with a B, and so this corresponds to 0, 0, 1. So what that means is that the Z piece is going to be empty. So I'm going to put these 2 chopsticks. These 2 chopsticks are the width, actually, let's see. Let's first get you all to agree that you're not going to complain about the width of the chopstick, right? You're only, if the slice of cake differs by the width of the chopstick, you're still going to be happy.
Sure.
Is that good?
Sure.
Okay. Also, I'm going to have you all agree that you're all hungry, right?
Well, yes.
Okay, good. So all of these are in agreement, so we can actually make this happen. Okay. Person B, that's you, right? Okay, so you get to pick first. This is the slice 0, 0, 1. So PZ, the rightmost piece, is the whole cake. Which is your favorite piece?
PC.
PZ, right? Yeah, that makes sense. Okay, so I'm gonna label this PZ is, I'm just gonna draw a Z here. Okay, let's find the next one. C. And I'm gonna use, let's see, let's see, okay. So we're gonna go from, right, when we go to the right, we're gonna keep our Y value the same, right? Y is gonna stay the same, and X is gonna go up. Which means that this piece on the left is gonna go up, right? I'm actually just gonna use 1 chopstick, because the Y piece is the same, the Y piece is still tiny, okay? C, who is that? C is you, okay, which piece do you prefer?
That one.
Still Z, okay, cool. And this might take a while. So let's speed things up a bit, and I'm gonna move this along here, and let's see, how do we want to do this? Let's see, I'm just gonna ask BCA, BCA. So, you know who's A, right? A, raise your hand. B, raise your hand.
No, it's
C, raise your hand. Okay, cool. Let's see, I'm gonna move this across 1, and you're gonna have to tell me whether you prefer this piece or this piece, right? Okay. Let's see, we're on A. A, which piece do you prefer? Can someone keep count, by the way? So can someone count, starting from, we should be at 3 right now, right? We should be at 3 right now. You're the 3rd person, we're at 3. Everyone keep count, 3. And each time we increase a person, we'll add 1, okay? So you still prefer Z, right? Okay, person B, which piece do you prefer?
Z.
Person C, which piece do you prefer?
Z.
A? B?
X.
You prefer X now? Really? You prefer this to this piece?
Yeah.
Okay, cool. Good. Thank you for saving me some time there. Okay, how many was that? How many people was that? 6, right? Okay, yeah, that sounds right. B, C, A, B, C. You're A, right?
What
Okay.
about B?
You're B. It can't be. That was 7, right? Okay. You're B. Okay, so Z, 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 and you prefer X. Okay, cool. Now we're gonna go up a little, right? We're gonna have a little triangle here, and so this, who should I be asking here?
Me.
Person C. You're right. Yeah, this is person C. Okay. And okay, what's gonna happen is we're moving this way, right? So we're actually moving along a constant x plus y line. It's like x plus y equals something. So basically, the 2 left pieces are gonna stay equal, but x is gonna go smaller and y is gonna get bigger. So what's gonna happen is this knife is gonna go a little this way, and now we have that. Okay, now you are person C. Do you prefer x, y, or z?
Z.
Z still. Okay. Okay. Which direction should we go? Should we go left or right? Right, right? Because we need to go through these trapdoors, right? So we're gonna go up here to this triangle. Okay, now we're gonna go to this point. So we're keeping, let's see, we are keeping y the same and increasing x. So what we're doing is we're moving this way slightly. Okay. And who am I asking here? A, right? This is A, person A. You're person A, right? Do you prefer X, Y, or Z? You prefer Y? This tiny piece? Are you sure? Okay. You're gonna get Y. And now what happened? We're done, right? We followed this trapdoor. Thank you, by the way. We followed this trapdoor, and we found the completely colored triangle. And so you, let's see. So basically, what happened now is you're okay with this piece. You are, and when this was here, when it was like shifted slightly, you were okay with this piece, right?
Yeah.
And when this was shifted slightly that way, you were okay with this piece,
Yeah.
right? And so is everyone okay with different pieces?
Yeah.
Okay, cool. And I'm gonna slice this up. We found our agreement. Okay, let me find a knife. Okay, that was cool. Here are some plates. Does anyone have any questions with how that went? Okay, cool. Let's see. This is gonna be very hard to split. So I
I only really wanted a carrot day.
huh?
I only really wanted a carrot part.
Not the carrot part. Okay, let's see. Let me.
So you can have the muffin and no beer. And Nelson,
Huh?
we have
Oh, sweet. Okay. Yeah, that would be helpful. Okay, I actually have more cake than just this. So let's see. I'm just gonna scoot everything over here. And then, thank you.
we have
Yeah, I have way more. Yeah, could I borrow that? Okay. I just need to make sure this gets split, like we agreed, so that this is fulfilled. Okay. So you were playing for who? You, right? So you actually get this. Can someone actually? Yeah. So you can start taking that, right? You can start distributing that. And
I don't really want to carrot.
you, I believe this is roughly more or less what you wanted. And you have the rest of this, and you can feel free to share it with whoever. And we actually have more cake. These are right. I actually sliced up a bunch of cakes for this. And yeah, we can. Yeah, we're gonna open this up. Yeah, if I could get some hands to help distribute this. Basically, yeah. Before this devolves into chaos, are there any other questions about this problem? I'm gonna hand out the cake eventually. About this problem, or about just if you have any general questions. If you have any questions about like any math thing, like learning math in like middle school or high school or college, As people mentioned, I'm an MIT student. I'm a math major there. If you have any questions at all, yeah.
When do you start learning this in school?
When you start learning this in school? What's really sad is that you never really get to experience this sort of thing in school. I actually learned this at Canada USA Math Camp, which is a really, it's a really like fun camp. It's a very fun summer camp for high schoolers. So once you get to there, I recommend you check that out. There's an application process. You have to solve some problems to get in. You have to write. You have to get some letters of recommendation to get in, but basically once you get in, yeah, you can see a lot of different cool math like this. Yeah.
So for the different, so if there are more completed triangles, is that how many ways you can slice up the cake? So have a third slice.
Yes, pretty much. Yeah, exactly. Each complete triangle tells you a way that to slice up the cake so that everyone's satisfied. Now, of course, there could be like points in the middle of these, right? Like where where actually it'll be different. So like there could be other points that aren't labeled that could also be feasible ways of slicing up the cake. But yeah, basically that's true. So, ooh, I've been talking for a while. My throat's sore. Any other questions? Do you have a question? No? No? Okay. Okay, I'm gonna figure out some way, yeah. I have muffins, I have this weird, like, we have this white cake, I have donut holes, I have destroyed carrot cake. Let's see, I have this leftover piece that Leo picked out. Let's see, I also have peaches if you are allergic to soy or something. You can take, let's see, I can actually, who wants peaches? One, do you want a peach? Are you sure?
Yeah.
You don't want anything? Okay, you can take a peach. Go for a peach. And we will split this up. Yeah.
Where did you go high school?
I went to Monte Vista High School. Yeah.
Junior high school.
Junior, I went to Kennedy. Yeah. Yeah, Kennedy.
That's what it's called.
Yeah. I went to school.
Do you recommend the science club at Kennedy?
Let's see. I was in science bowl for a bit. I'm not actually that familiar with the science aspect of thing. I tend to lean more towards math. But I've also heard good things, so I would recommend checking it out. Yeah. Okay. Yeah, but basically, just in summary, right? This is a cute little proof. I hope you learn some ideas of like how a mathematician goes about solving a problem. And this tends to be the sort of problems that you'll find mathematicians trying to solve, right? They're struggling with these sort of proofs. They're trying to figure out like, they're trying to prove that something exists, given some restrictions. How do you show that something exists? Given some sort of local behavior, how can you determine that some local behavior must exist, right? That's sort of what's going on here. You saw how we can model a problem like cake cutting really simply, right? Like this is a really weirdly shaped cake, and there are really weirdly shaped lines, and you might be trying to prove this for like some really general case, but basically what we showed is that you really only need to abstract this into some really straight lines, right? X, Y, and Z that add up to 1, that's all you needed to prove this, right? And so you can model this problem like this, and that solves it for you. Yeah, there's actually, if you Google Sperner's lemma, you'll find more things on this. You can also prove that every house, given a house, and some n friends and n rooms in the house, you can always assign a way to, you can always figure out a way to assign each person's, the rent that they have to pay, and assign each person a room such that no one is jealous of another person's room, and no one is jealous of the rent of another room. Right? As long as everyone wants to stay in a room rather than be homeless, and there are no closets, so there are no really bad rooms. And as long as no one cares about like fractional sets. Yeah, that's also important. That's equivalent to the Crum condition here. You can also use this to show that if you take a map of a place, right? If you took a map of Cupertino and you crumpled it up without ripping or tearing it, maybe it's on clay, so you could stretch it out, you could crumple it a little, and you threw it on the ground, then there's always exactly one point on the map that is exactly above the point it corresponds to in Cupertino, right? Does that make sense? So like, it's kind of weird. Like, basically there's a point on the map, right? Each point on the map tells you a point on the ground, right? Basically, and there's always going to be a point on the map that's exactly above the point on the ground it refers to. This is called Brouwer's fixed point theorem, and you can also show this. It basically also comes down to finding a completely colored triangle. Yeah. There are other things too. Oh, you can also prove that any square, if you divide up a square, there's something about a square. I can't remember the exact statement of the theorem, but basically, I think it's like you can't divide up a square into equal area triangles if there are an odd number of those triangles. Something like that. Okay. Yes, enjoy the cake. Take, all of the pieces are slightly different, so you can also have some muffins.
I need more.
Huh? Yeah, there's a lot. Yeah, if you have any questions, I'll stick around for maybe a little bit, and yeah, feel free to come up and ask. Yeah, let's see, if you email me at nelson.niu@gmail.com. Yeah.
Does anyone want more cake? Chris? Do any of the parents want cake? We have a lot of leftovers. I have Chris want cake.
But yeah, basically I taught this class a couple of times before, and I got pretty good feedback, except there was one person who, it was an anonymous form, and they filled out the form and they said, they only filled out one sentence, and their one piece of feedback for me was, there was no cake. So I brought cake this time. Yeah. Yeah. Let's see. So